Hello, this is Kayao Kaindak, Vice President of Marketing at Mokana, and welcome to the Mokana webinar, Securing Critical Infrastructure with Advanced Cybersecurity Controls. Today we have our guest speaker, Dean Weber, CTO of Mokana, and he'll be speaking about cybersecurity in industrial control systems and providing a deeper dive into how to implement strong security, from securing the boot process to communications, and also talking about secure updates. First, a little bit about Mokana. Mokana is an embedded security software provider, and we were founded in 2002, initially serving the military and defense market. We were building crypto controls that went into avionic subsystems, military aircraft, and vehicles. We've spent the last 15 years focused on securing industrial control systems with deep cybersecurity embedded down to to microprocessor boards and microcontrollers and chips. We are protecting more than 100 million devices today and are broadly recognized by a number of industry groups and analysts on our leadership in the industry. Our customers include companies like GE, Bosch, Siemens, Samsung, Panasonic, and Yokogawa, and we serve customers across industrial automation, aerospace and defense, transportation, and power and electric utility grids, and many sectors within critical infrastructure. Dean, our speaker today, Dean Weber, our CTO, used to be the CTO at CSC Global Cybersecurity. He's also been the CTO at a variety of companies, included Applied Identity, which was acquired by Citrix, and was a chief security architect at Teros, also acquired by Citrix. Sounds like a trend there. He has been involved in a number of different projects within the industry and spent several years in the U.S. Navy working in physical and electronic security. And Dean is a frequent speaker across industry events and a variety of cybersecurity programs and engagement, both in commercial and defense. So let me hand it off now to Dean, who will kick it off. Dean.
Sure. Welcome, everybody. Glad to have you here. Again, what we're talking about today is primarily the rise of incidents in critical infrastructure across, wherever you want to define those. It could be the 16 DHS. It could be the IIC referendum on security frameworks and foundations for critical infrastructure, as well as just industrial platforms. There's a number of ways to view the problem, but as we talk about it, basically we're focusing on industrial systems that are responsible for doing things in the industrial environments. I probably don't need to tell anybody on this call what the view of the world looks like. It's getting worse. As it relates to the industrial Internet of Things, we're in a perfect storm where, between Stuxnet proving that there is no such thing as a protected network at this point, all of our protections have been demonstrated to be able to be breached with significant enough effort, as well as the business requirements that we grant more access to the data being generated in these industrial environments for use with, analytics, predictive maintenance, mean time between failure, all kinds of things that the industrial people pretty much contained internally in years past that are now being part of the business decision on how to operate businesses. So, we have a lot of different surfaces on industrial systems, ranging from the physical, where, in disparate devices that may be distributed, to faraway places that are not easily accessible, all the way down to the way that industrial networks are typically designed and built, which is, you've got a you've got an endpoint or a field device, you've got an initial level of command and control, then you've got a roll-up of the command and control into an ICS SCADA network, and then you've got offshoots of that out into data report or data historian, and then outbound into the rest of the data analytics world, which could include on-prem, off-prem, hybrid analytics, meaning hosted by the local organization, a remote organization, or even up into the cloud. So we've got a lot of space that we need to protect here, even more space than we have in the traditional IT world. What Mocana is promoting here is that this is talking about protection versus detection. Protection means stopping or preventing things from occurring before they occur, as opposed to detecting and responding, which is the way that the IT world has traditionally done this. And this is a function of several different items, not the least of which is industrial systems are real-time. The valves may be opening, or flow meters may be measuring, or gravitometers may be measuring, or medical devices may be reporting on instantaneous conditions. It's a real-time environment. There's no time lag between the data being generated and the data needing to be acted upon. So applying traditional bolt-on security models in this world is going to be difficult. Not impossible, but difficult, and we promote that there is a better way to do this, which is actually getting out in front of the storm and preventing the transactions from being modified by external unauthorized sources, as opposed to trying to detect that they are being modified. Waiting for the slides to catch up. Okay, so I did a build out on the whole slide. The idea being is that there's a whole slew of things associated with the left side, which is the traditional IT, and the right side, which is the less traditional IoT and specific to the industrial IoT, where we have a lot of different measurements and requirements in terms of how we validate transactions, how we protect the environments themselves, and what kind of threats are being presented to them. So there is a raft of compliance issues currently, and I suspect a boatload of new requirements that are headed our way. One of the best examples that we have is the NERC-FERC partnership, public-private partnership between the U.S. government and the electrical providers, where an agreement was made that we could standardize together without heavy-handed government regulatory effort and comply with this or else type models, where we can agree on the measurements and we can agree on the control objectives and their results and what's working and what's not working in a forum, as opposed to a regulatory compliance environment. So, in all, I think that the industrial space is going to be looking more towards the NERC-FERC type models than they are going to be looking towards the audit and respond requirements that have been traditional in the IT world, although there's certainly a fair amount of that is going to come down on this as well as we extend SSIE 16 out to the operations of the IT in the OT. These are going to be, guidances and ultimately regulatory compliance issues that are going to be associated. We've seen new guidance from NIST. We've seen an evolving situation with Industry 4.0. We've seen 62443, specifically 3-3, and a number of other standards that are evolving and emerging on how this happens. And then over on the far right side of that, you've got the standards bodies like Trusted Computing Group, and then you have, what is becoming another element of risk to organizations, which is things like GDPR and data protection and data privacy in the EU, where GDPR has, now encompassed the fact that if an operator uses or deploys a technology which is known to be vulnerable and that vulnerability is exploited, that potentially they are at financial risk in terms of a fine, where the GDPR may authorize the controlling organization to levy some pretty substantial fines, like up to 4% of the gross revenues of a company for a year, which in larger companies could be a very big dollar amount. Or even to the fact that now that's even potentially being extended into the manufacturer, so that the manufacturer manufactures a product and sends it out, and an operator uses it, and they both know it's insecure, then there's the potential for both of them sharing in some of this financial risk. So we're seeing a number of different aspects of how things are being developed in terms of risk and compliance. I think that will continue over time. I think we'll see on this 853 R5 with some of the incorporated guidance from 888 and 863 being incorporated into that guidance specific to the industrial world. Moving forward. So again, in a model whereby we need to vertically align trust on a platform, that's what we're showing here, is how that could be done on a device, on a gateway, on a cloud, in kind of a three-tier model, where these are the elements of things that you need to put into each one of those devices. Right? You need to harden the endpoint to the point where you know if there is a modification, you know immediately that that modification was unauthorized, and that you have an opportunity to decide whether to trust the device or not trust the device. And then, of course, what do you want to do if you don't trust the device? Do you want to turn it off? Do you want to disable its interface for forensic analysis after the fact? Do you want to remove the certificates? Do you want to blow the certificate store away? These are all things that can be done on endpoints, on field devices, and then extended on into the gateway services, which are the aggregators, the data aggregators of these systems, these field devices. And again, you want to have a vertical trust model there. But between those two, then you also want the means to convey trust between the two in a bidirectional model. It's not just about the gateway trusting the field device. It's also the field device trusting the gateway. And without a full cryptographic trust model and measurement in place, you can make other decisions like, do I want to send data to this device, or do I want to aggregate data from this device? These are all things that are, potentially possible in a model where you're getting proactive in your defense as opposed to reactive in your defense. And again, what we're proposing is that cryptography has the opportunity to do that, particularly in the greenfield models that are coming out. Brownfield devices are going to be a little more difficult, not impossible, but a little more difficult to address because they weren't engineered for these types of services to be present. But that just means that we can start up a little further in the network, because there's certainly value propositions from all kinds of vendors in replacing ICS SCADA platforms with new, more efficient models to replace operating software in those platforms, and then moving down into the actual industrial networks themselves to replace the RTUs and the PLCs and the DCSs and the VSATs of the industrial working world post field device. And again, putting controls onto those platforms means that you can at least start the trust there. So this is Mocana's version of how we look at doing that. We start with a platform root of trust. That can be hardware, that can be firmware, that can be software. It could be, a TPM in a hardware world. It could be an MCU or PCU in an embedded world, or in a system on chip world. It could be a headless device that is built for purpose. It could be a software firmware design like TE TrustZone or Intel EPID SGX, all the way up into things like Java card technologies, where you're talking about SIMs, or you're talking about smart cards, or you're talking about SD micro cards that are being used as the primary root of trust for a designated platform. And then how do you leverage that going up the stack? How do you do a trusted BIOS? How do you do a trusted boot? How do you do a secure update process? We know from several of the last malware attacks that updates are a problem, right? In the traditional hash and sign model, you only have to compromise one set of certificates in order to overcome that, or you actually brute force the firmware itself, and you don't even get a signage and a hash value. You just push past those controls because they're not strong, like we've seen with Black Energy and like we've seen with some of the overload type technologies. So again, that's kind of where the baseline is in terms of the device and data integrity, and then going up into the confidentiality and transport layers. We've got all the traditional players there: IPsec, SSL, SSH, DTLS. And then, even into places where we have, very tightly constrained industrial environments where we're using group keys, GDOI, where there's a KDC and a number of public keys that are issued to an operating environment to create an authentication domain using just public keys. But the problem, of course, is also in those constrained environments, typically we're using UDP as transport, which means everybody can listen in. So we created a lightweight encryption layer for UDP that leverages the group keys so that we can make not only an authentication domain, but also an encryption domain of a very lightweight level that is able to be deployed in models like that. And then off to the right, is our cryptographic container. Again, what Mokana is known for and been in business a long time doing is small, fast crypto, specifically for embedded systems. And so again, we've got a fully FIPS compliant, or FIPS certified, I should say, FIPS 140-2 level 1 because we're software. We have participated in levels 2, 3, and 4 with other vendors. And we have 2 certificate management utilities that can be attached to that. One is the traditional OCSP SCEP, which is a problem for a distributed environment, right? It works a little better when you have a single IT shop or a group of IT shops where platforms are being developed. In the OT world, where the operator is taking devices from various manufacturers, they either have to set up a secure SCEP enclave and bring all those devices in for initialization and installation of trusted certificates, or they have to take OCSP and SCEP out to the devices. That's not an easy thing to do in the industrial world. So we've seen a lot of work being done on unique identifiers. I mean, even Intel EPID is an attempt at a non-standard unique identifier of a platform based on a secure element that Intel is embedding in their subsystem. But it's not an X509 certificate. You really can't create a full root of trust off of that. You have to equate that to something further down the road. And I'm not saying that's bad. I'm just saying that that's an alternative to OCSP and SCEP. Well, in the meantime, there's been a number of players in the world that have gone out and said, that we really, we've invested all this effort into PKI and into X509 certificates, and it's really the right way to go. So how do we overcome this problem of SCEP locally or remotely? And the answer for the industry was an RFC that was written about 6 years ago, was ratified about 3 years ago, called RFC 7030, which is enrollment over secure transport. Enrollment over secure transport is all about being able to do all of those OCSP SCEP functions securely over the wire or over the air. And we provide the ability to do both. And then at the very top of that, we have all of the new key interface work for IKV2, as well as all the new NIST guidance for key entropy and key padding. And then a suite of extensible authentication protocols. So this is a diagram of how the solution set actually gets deployed in modular format, where we have the capability of doing the basic cybersecurity, enhanced cybersecurity, and premium security that is all aligned with FISPA low, medium, and high, or it's aligned with Industry 4.0, and level 2, 3, and 4, or 62443 3-3 level 2, 3, and 4. The IIC security reference framework also has the concept of levels. This would also be levels 2, 3, and 4, where level 1 or level 0 and 1 are traditionally no or low security elements that are baked into the platforms. So again, this is all based on guidance from governments, guidance from industry, guidance from regulatory elements and consortiums, where you have a design concept that you have to build to in terms of what the security of the platform or the gateway or the service or the remote elements have to be validated to, and then you can apply the right security controls based on that. Mocana's design is around embedding each one of those elements in basically 4 different container models, hardening the platforms with standards-based encryption and key interface, securing the boot process. So if an element had like a Windows 10 on a bare metal platform today requires access to a TPM to hardware qualifier or hologram, which is great. But the consumer of that trust model is exclusively Microsoft, right? It's not shared with the application. It's not shared with the platform. It's all about the security of Microsoft, which in itself is great since Microsoft has traditionally been a very large target for malicious intent. But it still doesn't take into concept the supply chain of the platform or the supply chain of the application softwares or even the outcomes of those functions on platform. It's really designed to just be supportive of the Microsoft operating environment. And we really should include that in the broader scope of the platform security, not just the OS security. So securing the boot process is one way that gets started, and you can do that through validation of the BIOS, validation of the firmware boot structures for boot, bootstrap loader, kernel load, kernel utilities, et cetera, depending on how far you want to go with it. We can include those measurements, cryptographic measurements and validations to create that root of trust. And then moving to the right is integrating both those hardware tools with the software tools. So not trying to displace what Microsoft's doing, but to take advantage of what Microsoft's doing in the broader concept of platform trust. And then last but not least is the ability to convey that. And ultimately, the ability to convey that becomes part of the decision process of whether you want to trust it or not. So if it gives you a trust value, a cryptographic value that is proven trustworthy at the binary decision level of it is good or it is not at the cryptographic level, then determining whether or not you want to continue to communicate with it or what you want to do about the communications level or how trustworthy you want to how much trust you want to assign the data being generated. Those are all things that can be done based on an empirical, discrete level of knowledge of the trustworthiness of a particular element in the overall solution set. Moving on. So getting into the nuts and bolts of this, taking in the concept of what a traditional industrial framework looks like, where we have field devices, we have intermediate services, then we have ICS SCADA platforms, and then ultimately we have the potential for analytics to be part of ICS SCADA or to be external to that. And I think more and more people are leaning towards external just because of the sheer power of the data analytics that can be brought to bear through other means, through other data analytics platforms. So again, obviously this is a fairly broad range of solution sets, but each one of these devices has the capacity to be measured, and each one of these devices has the capacity to not only create and deploy a trust value, it also has the ability to consume a trust value. So whether it's a peer-to-peer network or a client-server network or a 3-tiered device to gateway cloud environment, all of these can have a secure element. All of these can have a secure operations capacity with a empirical measurement that represents that the platform is trustworthy or it is not at the cryptographic value and at the strength of the crypto chosen. The big thing here is, again, we talked about this a little bit earlier, which is, the device security itself becomes problematic the further out in the chain you get. The less processing horsepower, the less storage, the less memory and operating footprint of the platform. So being able to use something that is very small and very fast on a restrained or constrained device out in the field, and then being able to use that same basic construct in an industrial gateway or on up into an industrial analytics platform is important from the aspect of interoperability. There's standards-based communications between these 3 elements, field to gateway to operations and on into analytics. It's important that we have the ability to interoperate these at a standards level. Improving safety and reliability. So, those of you that are in or have looked at the industrial world understand that risk is measured differently in the industrial models. Risk is measured in typically loss of life in the industrial world, where elements of risk are C1 at less than 50 bodies, C2 at 51 to 500, and C3 at 500 or more, or whatever the particular measurements are for the target environments. Again, versus loss of IP, loss of reputation, loss of financial status, all of which also can be included. But the real ones, the industrial world's more like the DoD world, where decisions, real-time decisions or near real-time decisions, result in risk to people. And so that's why the driving force on the industrial world is towards safety and reliability above cybersecurity in the past. And obviously, again, things like Stuxnet have changed that, because now there is significant risk associated with cyber to offset or be part of the same measurements that are safety and reliability. So being able to get these things interworking and interoperable is fairly important, where whatever we do from a cyber aspect, it cannot detract from the safety and reliability of the manufacturing elements. It actually should add value, not just be a standards-based, sorry, I went too far, a standards-based model where we have the ability to have all of these devices not only intercommunicating, but being able to assist in the safety and reliability functions of the device. Obviously, making it resistant or making it impervious to cybersecurity manipulation or malicious manipulation from peer or near peer or nation-state level attacks. We also have to be worried about just the normal day-to-day operations. If that switch doesn't work and that valve remains open, then things can blow up. Or if that operating theater in a hospital doesn't remain integrated at a trustworthy level throughout the operation, then the patient could have adverse consequences. These are the kinds of things that we have to be concerned with when we talk about cyber as applied to industrial, to include the safety and reliability functions. All right, so a couple of use cases here for those of you that are architects. So device enrollment, we started talking about this with what we do with EST. The traditional world is you either have to bring the element to a OCSP SCEP enclave, a trusted enclave for secure installation of the certificate. What that doesn't do for you is it doesn't let you manage that certificate remotely, right? You still either have to bring the device back in to manage that certificate, or you have to take the OCSP SCEP process out to the field and put somebody, out in the oil field or up in the rafters, or out on the catwalk of a refinery or whatever that's going to be. So the ability to do remote management, installation, and updating of certificates as deployed in a model where certificate chaining, where X509 trust chaining is the primary mechanism by which we evaluate these platforms, is very critical. If you, as an example, if you look at the United States government struggling with the removal of the SHA-1 hashing algorithm because it's been broken for, going on 2 decades now. I think NIST issued guidance about 10 years ago that government should cease using it and should cease providing it as an option. And yet the government itself can't actually mandate that because they can't get to the certificates in order to be able to do that. They can't remove that. So a lot of negotiation down to SHA-1 is successful. Well, using a certificate management platform, you could actually, without replacing the certificate, you could actually update the certificate to say, don't auto-negotiate to SHA-1. So if you get a SHA-1 request, redirect it to SHA-2 or whatever. But these are all management philosophies that are prevalent in the X509 world, and we just have to find mechanisms by which to apply. And the device enrollment model is where that starts, and EST modeling is where that's really prevalent and important, because we want to be able to not only do secure installation, we want to be able to do lifetime update or certificate update, or ultimately, certificate revocation or certificate end-of-life removal or replacement. Again, all of these functions need to be done, and you don't want to have to drag OCSP SCEP out to the device or drag the device back to OCSP SCEP. And your other option, of course, is to manage the certificates in an insecure fashion, which is also one of the reasons why we've seen so many certificate invalidations over the last few years. Again, the idea here is to create a chain of trust of the devices, creating the model whereby they are vertically enhanced with cryptography to create a trustworthy at the strength of crypto measurement model, and then moving over to the right, how that works in terms of the OEM and how they can take advantage of that and use that as market differentiator and market validation in order to meet their customers' demands for more secure platforms. And then moving further to right, how the operator or the operator in conjunction with the manufacturer can actually do the device enrollment and the certificate management, and then all the way up into the services provisioning over on the far right-hand side. And all of this can be done through something like an EST. It can also be done through OCSP and SCEP, but again, there's limitations to what that can do. Second use case is enabling secure updates. By secure updates, we're talking about the ability to do updates, hardware, firmware, software, could be change of configuration, whatever. And traditionally in the industrial world, that's done today through hash and sign. And while that's better than doing it clear text with nothing behind that, a better way of securely updating is, for example, Black Energy found in the Ukraine, the update process itself was circumvented and firmware was rewritten in edge devices and in gateway devices. Excuse me. And that would have caused problem had it not been detected and removed before the system was brought back online. And luckily enough investigative resources were promoted there that could actually be done. But that's not always going to be the case. So enabling a more secure update facility across the enterprise is important. Again, because we're in the crypto world, being able to create a full cryptographic container, a PKCS envelope, if you will, to install the certificate within, or install the update within, or install the operands necessary for the update, or the files necessary for the update into a cryptographic container, not only gives us the ability to encrypt that against the client-side certificates, we can also do remote attestation and multi-signatory on that encrypted container. So, let's say it's an Infineon TPM that's being updated. So Infineon's going to sign the update and distribute it, and it's targeted at an Intel subsystem. So Intel's going to want to countersign that update saying, yes, it's approved for use on our Intel subsystem. And then the device manufacturer comes along and says, using the Intel subsystem, let's go do something with that. And then ultimately, if that changes, then the device manufacturer may want to also have knowledge of that update. And then last but not least, the operator, the actual consumer of the technology and the operator of the technology is probably going to want to know that updates are being provided. So using that model, you would have 4 signatories, 4 code signings, if you will, from root certificates associated with those 4 different elements. And a secure update process could then actually validate that all 4 of those signatories were present and that the signatures themselves were valid prior to unencrypting the payload and installing it as a remote update. So these are all things that can be done using technologies today. So these are things that we want to look at going forward into how we establish more secure operations, which brings us to the next use case, which is secure operations. And again, this is the whole model of how one creates a secure ecosystem, from certificate creation to installation, and then ultimately to validation of the transport mechanisms and all of the pieces that fit in there. And this could be, again, various forms of root of trust. This could be various mechanisms by which certificates are managed and mandated and ultimately retired. And then also the cryptography that is in use to actually validate how all of this works, and the ability to get to a registration authority or get it to an HSM or get to a certificate intermediary where the signage can be validated, that the keys are good, the certificates are good, that the signer is good, et cetera, et cetera. And this is how all of this stuff snaps together in real use cases. So I've talked about 35 minutes now, and I think we're going to go back to Kayao, and then we're going to open it up for questions and answers.
Great, thanks, Dean. If you do have a question and you would like to, you should submit that in the Ask a Question within the BrightTalk site there, right below the presentation. If you're in full screen, you'll have to get out of full screen and just type in your question. We do have a few questions here. One of those is, with the Trump executive order requiring the healthcare private sector organizations to meet various standards, can you comment on NIST in particular, or any kind of NIST-specific criteria?
So, again, as we talked about in broad strokes, well, first of all, let me disclaim that I am not an authority on the executive order application. I think it is very subjective still in its design. I think more will be revealed as people actually start working with the application of the executive order after all the reviews. At least that's the hope. The reality is, whether you're trying to comply with HIPAA or whether you're trying to provide secure elements and secure validations for the chemical manufacturing facilities under some of the stuff that DHS has mandated, or if you're in the European community and you're just trying to get compliance for 62443, the security precepts that NIST and all of these others are based on are pretty much standard in goal. They may not be the same control objective as defined. They may not be given the same latitude in terms of compliance. But NIST 853-R4 specifically gives a consuming organization, particularly a United States entity, to have wide latitude. So if you are, if you correctly rated your application at a FISMA level, at the levels of confidentiality, integrity, and availability at the FISMA low, medium, or high level, and you have correctly chosen the right level based on the guidance, then you go over to the NIST 853 and you pull the guidance column, which is additive. So if it's FISMA low, then it's just the first column. If it's FISMA moderate, then it's the first and second column. But there's a group of control objectives published in groups, access control, access management, firewall and border protection capabilities, et cetera, et cetera. That's a sound security foundation built primarily for the IT world, but now with supplemental guidance coming out for the OT world to include healthcare and likely to include places like automotive. So the point that I'm making there is that I think all of the cybersecurity baselines are going to be relevant. What will be interesting to find out is how strong they make them. And again, using the NIST example, so you pick the control objective and you demonstrate the control objective has been met as a primary control. Or if you can't do that, then you have to show that you've built a compensating control. Or if you haven't do that and you actually do want to comply to it, then you have a POAM, a Plan of Actions and Milestones, that actually takes you to compliance or creating the control objective or the compensating objectives. And if none of that works, then you can still accept the risk. You just have to do that in writing, so that if that risk is then exercised and you become vulnerable as a result of that risk being improperly accepted, then you're the responsible party. And in government, that typically means censure or firing. What that's going to mean to healthcare, I think we're going to see similar transactions in all of the critical infrastructure world. Again, the cybersecurity precepts that these things are based on are pretty much all the same. Their definitions are a little bit different. Their risk objectives are a little bit different. Their compliance objectives may even be a little bit different. But the precepts, the actual secure elements that all of this is based on, is not that different. So the short answer to your question, after being long-winded, is yes, I think that some of the private sector organization healthcare requirements will be based on things like NIST. Do I think the government's actually going to provide a NIST checklist? to private healthcare? No, not anytime soon, anyway.
Okay, we have another question, and that is, can Mocana be used in gateways or only endpoint in ICS devices?
Mocana can be used anywhere. I mean, you can use this on a full-blown computer if you want. The problem with the cyber measurement model, the cryptographic measurement model in a full-blown computer is that typically it's filled with a lot of things that are not used on a daily basis, bloatware, et cetera. You know, I mean, the Microsoft operating system as an example, you know, this is why whitelisting never came to full value fruition, was because whitelisting an entire disk full of operands and executables and file system boundaries was just impossible. I mean, I did some work back in the early days with Wyatt Starnes and SignaCert and Tripwire and some of the stuff that we were trying to do back then. We couldn't build a big enough manifest of all of the softwares, firmwares, and hardwares installed in a general purpose computer in anything like real time. So the advantage of the industrial world is it's much smaller, it's much faster, and it is much more focused on real time, and therefore willing to expend the effort to actually get real-time validations. The further out into the commercial world you get, the less likely that's going to happen because of the sheer size and magnitude of the problem set. Not impossible to do, and as new processors and new processing power comes online, as well as new cryptographic capabilities like the advancements in AES-NI or the cryptographic offloads of things like MCUs and PCUs and Cavium and some of the other dedicated fit-for-purpose cryptographic offload engines, I think you'll see that we can do more and more towards the more traditional computing environments. But the short answer is the industrial world is focused on real-time from the field device all the way up to the edge of the ICS SCADA world. Beyond that, out into the cloud, then you have a little bit different scenario where the cloud architectures, while they're based and steeped in IT architecture, the workloads themselves, the virtualizations or the containerizations actually have more focused efforts. So what's going to occur inside those models is going to be much more constrained and much quicker in terms of near real time than a traditional operating environment standing out in the cloud architecture. So I think we stand the opportunity to actually extending this pretty well into those spaces through things like TPM remote attestation, and ultimately to be able to get as part of the DevOps model for containerization or virtualization to actually get the author's attestation into the model and then have an ability once deployed to validate that attestation as being locked and not subverted or modified in any way that would cause you damage at the point of initialization, whether that's a VM spinning up or whether that's a container opening.
Okay, Dean, we have one more question, and so we need to, and then we're going to wrap this up. How is the rise of cloud computing impacting the critical infrastructure industry's field?
Well, cloud, again, as I started out this conversation talking about, cloud brings an aspect of power to the analytics that is, potentially going to be needed in order to analyze the broad swath of products that are in IoT and specifically in IIoT. So the cloud as a compute platform has dense virtualization and dense computing capabilities where we can apply that horsepower to the problem sets associated with all of the disparate elements of data that are being generated in the industrial or commercial Internet of Things.
Okay, hey, real quick. We have one last question. Just a few seconds on upgrading brownfield devices with multi-factor authentication.
Sure. So some devices will have the overhead and capacity to do that. Some may need an external intermediary for things like remote attestation. Some may actually not be able to be upgraded because they were so built for purpose that they physically don't have the headroom, they don't have the horsepower in the processor or memory or storage to actually be able to take on any additional functions. So there's grades of brownfield, and some will and some won't be able to be upgraded to take advantage of these types of technologies.
Great. Well, thank you very much, and thank you all of you who were able to join this webinar. And there is more information available at mocana.com, as well as links within this webinar. Thank you very much, and have a great week. Thanks, Dean.
Thank you. Thank you, folks, for listening.